Alright guys, so in this video I'm gonna give you a live demo regarding how to use our quick modeling solution to build a structural model, facies model, and petrophysics model. Before we get started, I would like to introduce this project over here. So as you can see here, for this project, we have a bunch of wells. So this is a 2D map. We have a bunch of wells sitting in the middle, and we have four polygons coming from two individual horizons. And if I move to the 3D window, you will see it better. So here, so we have the wells sitting in the middle, in the crest of the structure, and then um, the four polygons actually going through the entire structure. And we also have two seismic interpretation horizons. The first horizon is the semi-transparent surface on top, and there is another horizon at the bottom. So what we're trying to do is to build a model that can give us a description into the volume constrained by these two horizons. Okay, and also we have in this project we have four different horizons. Let me make this bigger. So we have H1T, H2T, H3T, and H3B. So those four horizons. And the first and last horizons are actually the ones I show you on the 3D window. That's from seismic interpretation. And from well logs, we can also identify H2T and H3T. So in our model we're gonna have four horizons, and in between the four horizons, we have three different zones. So that's the project. So to access our quick modeling tool, we need to go to structural modeling and then click one button. As you can see here, this is a very simple interface. It's very straightforward. So you need to enter the model name and boundary and stratigraphy, which is our well pics, as the input data. So in this case, I will give model demo. Okay, and the boundary, we have a boundary polygons predefined in this project, and then stratigraphy, and this is actually my four horizons. And then also we have two fault polygons as I shown in the 2D window. So the first step is to create fault model. As you can see here, we have fault model, and then we need to create a horizon model, and then facies model, and then petrophysics model. So from left to right, that give us the workflow to build structural model, facies model, and petrophysics model. So the first step is to create a fault model. So I check the input data and then hit create. Okay, so let's take a look at the results. Let me just use this 3D window, and then I will just clean up the window and go to the model management. And you can see here we have created a model data tree called model demo. And then we have created the fault pillars in here. So that's my fault pillars we just created using the two fault polygons. And then the next thing is, usually when we have the fault interpretation result from seismic data, it's probably not as ideal as you would expect it to be. So in that case, we need to optimize the fault surface. In this case, we have a dominant fault from north to south, and then we expect that the dominant fault would intersect with the other fault over here. But in fact, when we first create this fault model, initially these two faults do not intersect. Of course, we provide you with the interactive tool to adjust the fault geometry so that these two faults would intersect. But in here, we also provide you with the fault surface optimization tool over here. So in here, you need to set up the parameters like for the horizon extension, vertical extension, maximum distance for intersection, etc. Once you set up the parameters, you just hit optimize. Then the fault geometry will be will be fixed automatically for you. So I will hit optimize here. Just pay attention to whatever happened in this area. Okay. Okay, now let me close this window. As you can see here, this fault, the dominant fault, has been extended and intersected with the other fault. This might not be very difficult if you just want to do it by hand, but what if I rotate to the other side? As you can see here, we have three faults coming together. So if you want to add it by hand, you can still do so, but it's extremely difficult when the geometry becomes relatively complex. So using this function, fault surface optimization function, is actually pretty helpful when dealing with complex geometry. Okay, now we finished the fault modeling. Let's move to horizon modeling. So the horizon modeling, the first thing we need to do is to give a grid name, because at this step we start to create the geocells. Okay, I will use grid 01 as the name, and 30 and 30 as my grid size. That's for INJ. Okay, so for horizon modeling, as you can see, by default there are 4 different horizons. Those are actually, if you remember, those are actually the 4 horizons coming from well pigs. And we also know that we have 2 horizons with the seismic interpretation result. That's H1T and H3B. So in that case, we will check the key horizon. Then we're going to use the contours from seismic interpretation as a constraint for my model building. So once you select the data, you can go ahead and click modeling. Okay, now it's complete. Let's take a look at the results. Clean up the window, and then as you can see here, we created a data tree called grid01 here. And let me first take a look at my fault surfaces. Now this is the fault surface based on the corrected fault model. And then we have 4 different horizons created. I'll just show you one horizon over here. So that's the first horizon from that well pigs. As you can see, because we have the fault polygons, now the horizon has been broken up to demonstrate there is actually big displacement due to the faults. And of course, because we have 4 different horizons, now we have 3 different zones. Okay, so that's my zone model. If I open up the grid over here, okay, so I turn on the grid, as you can see here, my I and J actually settings here actually controls the grid size on the I and J direction, but on the K direction, which is our vertical direction, we haven't done the layering yet. So which means that for each zone there is only 1 layer. So the next step, we're gonna do the layering over here. So right now I'm using the method number of layers to define how many layers per each zone. But you can also use different kind of methods so that you can define the layers by specifying its thickness, etc. Okay, so in this demo purpose, I would just do the demonstration for the first zone, so that I would just do the layering for the first zone. And for the other 2 zones, I would just use 1 layer. Okay, and then I would just do layering. Now you can see, after I finish layering, the layers for my first zone has been created. So there are 28 layers. And you can also see here on this table, it calculates the mean thickness for each zone. So in that case, so the layers here about 0.5 meters per layer. So that completes my structural modeling. Let's do facies modeling here. And for facies modeling, the first step we need to do is to create the facies block well. We select the facies log, which we have over here. And then what this step means is to create, to populate our facies log to the individual grid blocks that are passing through uh, the wellbore. Discretize. Once it's finished, we can check the results. Now you can see there is a block well property grid data tree created. Now we have the facies block well over here. So those sticks are actually the grids that's passing through the wellbore. Okay, so the next step is to populate this block well to the entire reservoir so that we can see so that we can build a facies model in the reservoir. So as I said, I just want to do the modeling for the first zone. So I will just lock the other two zones. Okay, so let me go back to the first zone. And then I will use the method sequential indicator simulation for this modeling. So by default, the three facies I have in my model, the proportion is coming from the block well. But we all know that this number could be a little bit misleading because the reservoir, the facies distribution, the facies proportion in the reservoir might be different from what we see from the wellbore. In this case, I will use 73% as my channel facies, and MCB is 9%. So the summation of these three facies will be 1 total. Okay, so now the next step is to set up the variogram parameters one by one. To save time, I already have a set of parameters, but if you want to know how to set up the variogram parameters, we have a variogram analysis tool to help you identify the key parameters used in variogram analysis. So for clay, I will just keep everything as default. And for channel, I will use major range 530 and 430 as my minor range, and vertical range 6, nugget 0, and azimuth 175. Okay, then I move to MCB. MCB is actually mid-channel bar. For that, major range is 480, minor 420, and vertical range 4. Still nugget 0 and azimuth 175. Okay. And then in the settings, I will check this reduce noise, and then come back to mid channel bar. In the trend, I'm gonna use my facies map as a constraint to train my geological model. So I check this facies map data, and then check this. This is actually my facies map for that zone. Okay, so after I set up everything, I will just hit run. It's actually going to take about a couple minutes because now we are using constraint, using facies map as a constraint. The thing is, if we don't have any constraint, the simulation will be really fast. And other things I would like to point out is that facies map is just one type of constraint. And you can also use surface constraint or 3D. 3D is basically my seismic attribute. You can use the attribute as a constraint to train the model as well. All right, now the simulation is done. Let me close this window and then clean up this window. And in the property model, there is now this facies model over here. Okay, now this is my facies model. Actually, I would like to show you side by side of this facies model versus my facies map. So if I go back to data and open up my facies map over here and put this window side by side, now you can see my facies model agree pretty well with the facies map over here. And of course, you might ask, what's the vertical variation of this facies model? Well, then I can use the model view tool over here and then go in layer by layer to let you see the vertical variation of the different of the facies. So as you can see there, there's a lot of variations in the vertical direction in the facies. Okay. All right. So that's my facies model. Next, I would like to create a petrophysics model. So in this project, I'm gonna create a porosity model, and also I'm gonna use my facies model to constrain my porosity model. Similarly, the first step to create a porosity model is to create a porosity block well. So I have the porosity log over here, and then I'm gonna use a arithmetic average algorithm to create the block well. And then I will just do discretization. Okay. And in here, in block well, we have the porosity block well. Now, as you can see here, these are the porosity values assigned to the grid blocks that are passing through the wellbore. The next step is to populate this porosity value to the entire reservoir. Again, I would like to do the modeling for just the first zone. So I'm just locking the other two zones. Okay. So I will check facies because I'm going to use my facies model to constrain my porosity distribution. And for my algorithm, I'm going to use a sequential Gaussian simulation. So again, there are three different facies. I'm going to set up the parameters for each of these facies. For porosity, usually we have this normal distribution in the reservoir, so I check normal. And then the porosity range for clay, I will use 0 to 5%. And again, I'm going to keep everything in variogram settings as default. Then I move to the next facies, channel facies. Still sequential Gaussian simulation and normal distribution for the value. Channel, I'm going to use 8% to 25%. And for the variogram, I still want to use the same settings as in the facies. So 530 for the major range, 430 for the minor range, and 6 for vertical, nugget 0, azimuth 175. Okay, then mid channel bar, normal distribution. Porosity range is from 5% to 15%. Variogram parameters 480 for major range, 420 for minor range. Vertical range is 4. 0, azimuth 175. Okay, so that's all we need to do for this demo. There are other settings, of course. Well, you can still use trend to do the simulation, but right now we only have the facies model as our constraint. Okay, then I just hit run. Okay, now the simulation is done. Let me take a look at the porosity distribution. So that's my porosity distribution. If I open up another 3D window and bring in the facies distribution, the facies model, and then put this window side by side, you can see that the porosity distribution is well controlled by the facies distribution. See here, we have very low porosity, almost to 0. That's because we have clay facies. And for example, over here, we have a relatively low porosity that's around 10%. That's because we have mid-channel bar. Mid-channel bar, if you remember, the porosity distribution is between 5 to 15%. So here, I've shown you that you can use the facies model to constrain your porosity distribution, the porosity model. That's a entire workflow to use this one-button geological modeling module to create a structural model, facies model, and petrophysics model. As you can see, it's very fast and it's very straightforward. We expect to spend about 2 days to train our users. And then after that, depends on how complicated your problem is. Usually the users can spend between 1 to 3 days to finish a geological model. I hope you're enjoying this video, and let me know if you guys have some other questions. You can visit us at www.gptsoft.com. Thank you very much.